Examples on vector subtraction. In this lecture, we will discuss some examples in vector subtraction. First of all, we must understand where do we use vector subtraction in physics. There are primarily two places where we use vector subtraction. First, whenever we want to find change in any vector quantity. Change is always defined as change in value of a quantity is equal to final value minus the initial value of the quantity. For example, change in velocity delta v vector will be equal to vf vector minus vi vector, where vf is the final value of the velocity and vi is the initial value of the velocity. Change in acceleration delta a vector will be equal to af vector minus ai vector. Change in momentum delta p vector will be equal to pf vector minus pi vector. Notice here that delta v is a new vector. It will have its own magnitude, it will have its own direction, which will be different from the magnitude and direction of vf and vi. Similarly, delta a is a new vector whose magnitude and direction will be different from the magnitude and direction of AF and AI, and delta P will have different magnitude and direction as compared to magnitude and direction of PF and PI. Therefore, vector subtraction leads us to a new vector which is different from the original vectors. The second place where we use vector subtraction in physics is when we want to find the relative velocity of one object with respect to another. The relative velocity v dash is defined as v dash is equal to v minus u. We will discuss this in detail while we discuss the concept of relative velocity in kinematics. So now let us solve some problems to understand how do we apply vector subtraction. Suppose there is a car which is moving with the speed of 20 meters per second towards right. If the car is speeding up, after some time the speed of the car will become 30 meters per second, and we want to find the change in velocity. Delta v vector will be equal to vf vector minus vi vector. How do we subtract vectors? We place the tail of two vectors over each other, and the third side of the triangle represents the difference of two vectors. We take the vi vector and place the vs vector tail on the tail of vi vector. Vf vector minus vi vector will be the line joining the head of vi vector with the tail of vf vector. This is the delta v vector. As we can see, it has its own direction which is towards right. It has its own magnitude which will be 10 meters per second. Thus the change in velocity is 10 meters per second towards right. So now let us discuss a little bit of physics involved in this process. If the speed of the car is increasing, we can tell by experience that the force required to do so will also be towards right. And we see that delta v, the change in velocity, is also towards right. Thus in this case we see that the force applied on the body is in same direction as the change in velocity of the body. Is it always true? Yes, it is. And we will learn this in Newton's laws of motion. In the next example, let us say the car is slowing down. Initially, it was moving with a speed of 30 meters per second, and after some time, the speed of the car reduces to 20 meters per second. Question is, what is the change in velocity? We want to find delta v vector, which will be equal to vf vector minus vi vector. To subtract two vectors, we place the tail of two vectors over each other and find the third side of the triangle. Thus we place the tail of vi and then we place the tail of vf over the tail of vi. Vf vector minus vi vector will be the line joining the head of vi with the head of vf. So this is the delta v vector whose direction will be towards the left in this case, and whose magnitude will again be equal to 10 meters per second. So change in velocity delta v vector, it's a vector which has its own direction, which has its own magnitude. In this case, the car is slowing down. We know from experience that the force required to slow down a car will be towards left. The change in velocity delta v vector, as we have seen, is also towards left. Here again we see that the change in velocity is in same direction as the direction of the force applied. Next example 3. A ball of mass 2 kg moves with 4 meter per second velocity towards a wall and rebounds with the wall with a velocity of 1 meter per second. Such collisions are called as inelastic collision. The momentum of a body is defined as mass into velocity. So the initial momentum of the body will be equal to 2 into 4, 8 kg meter per second towards right. And the final momentum of the ball will be equal to 2 into 1, 2 kg meter per second towards left. The question is, what is the change in momentum? So we have to find Pf vector minus Pi vector. Pf vector is towards left and Pi vector is towards right. Remember that momentum is a vector and therefore will add and subtract like a vector quantity. How do we subtract two vector quantities? We place the tail of Pi over the tail of Pf. Third side the triangle from the head of Pi to the head of Pf will be equal to the change in momentum delta P vector, which will have a magnitude of 10 kg meter per second and will have a direction towards left. If we look into this case, it is very easy for us to figure out that the wall will apply a force towards the left on the ball, and we see that the change in momentum is also towards the left. This is the result which is also going to be always true, that the change in momentum of a body will always be in the direction in which the external force is acting on that body. So the force acting on the ball is towards left by the wall. The change in momentum of the ball is also towards left. In the next example, example number 4. Here a body moves with a velocity of 4 meter per second towards east, and after some time the velocity of the body changes to 3 meter per second towards north. Thus Vi vector is 4 meter per second towards east and Vf vector, the final velocity, is 3 meter per second towards north. The question is, what is the change in velocity? That is, we have to find delta V vector, which will be equal to Vf vector minus Vi vector. The change in velocity will not be equal to 1 meter per second. Velocity is not a scalar quantity. The change in speed will be equal to 1 meter per second. Always remember that velocity is a vector quantity and therefore will add and subtract like vectors. And how do we subtract two vectors? Here we have to find Vf vector minus Vi vector. We place the tails of two vectors together and find the third side of the triangle from the head of Vi to the head of Vf. Thus placing the two tails together by shifting 3 meter per second vector, change in velocity delta V vector will be given by the third side of the triangle. The magnitude of this vector will be equal to 5 meter per second. Thus the change in velocity is actually 5 meter per second. Notice that the change in velocity is a new vector in itself with its own magnitude and with its own direction. Next example, example number 5. A particle is moving in a circular path with uniform speed. The speed is therefore constant, but the velocity will always be changing because the direction is changing as the particle moves in a circular path. Let us take a point on the circle. The velocity at that point will be tangential to the circle. Let us say the velocity is Vi at this point. After some time, the particle moves away to a new position and its velocity changes. The new velocity will be along new tangent at that point. Let us say Vf vector. Notice that the magnitude of Vi vector will be equal to the magnitude of Vf vector because the speed is same. But we cannot say Vi vector to be equal to Vf vector because the directions are different. We want to find change in velocity. Delta V vector equal to Vf vector minus Vi vector. How do we find change in velocity? We place the tails of two vectors together. Third side of the triangle will be the change in velocity. In this case, let us shift the tail of Vf vector and place it on the tail of Vi vector. Delta V vector will be the line joining the head of Vi with the head of Vf. Thus, we get the change in velocity to be delta V vector. This is a new vector different from Vf and Vi, both in terms of magnitude and direction. If you notice, you can see that delta V is roughly towards the center. Change in velocity is therefore towards the center. We have seen earlier that force will always be in the direction of change of velocity. So in this case also, should the force acting on the particle be towards the center? Yes, it is. Haven't you heard of centripetal force? In this final example number 6, a particle is projected from the ground. The path followed by the particle is called as parabola, and the motion is called as projectile motion. As the particle moves in air, its velocity changes in both magnitude and direction. So in this case, both the speed and the velocity changes. In the previous question, only the velocity was changing, not the speed. The speed decreases as the particle goes up, and it decreases as it comes down. The velocity direction is always tangential to the path, and it will be continuously changing. Let us take a point I. The velocity at that point will be tangential as shown. Let us call it Vi. At the topmost point, the velocity will again be tangential. Let us call it Vf. In this case, the magnitude of Vi will not be equal to the magnitude of Vf. In fact, the magnitude of Vi will be greater than the magnitude of Vf, because we know that any body slows down as it goes up, and further, as the particle moves up, the direction in which it moves also have changed. So Vi vector cannot be equal to Vf vector, both in terms of magnitude and direction. How do we find change in velocity? We want to find delta V vector equal to Vf vector minus Vi vector. How do we find change in velocity? We join the tails of two vectors. Let us join the tail of Vf with the tail of Vi. The third side of the triangle from the head of Vi to the head of Vf will be the change in velocity. So this is the change in velocity delta V. Delta V is a new vector with its own magnitude and direction. As we can see, it is downward, and therefore we can conclude the change in velocity as the particle follows a projectile motion is downward. Can you guess in which direction is the force acting on the particle as it moves in the air?